Hi, we're going to check if a particular set of bits are set in a given state of bits. This would be really trivial if not for the fact that we're given our query bits and our state bits as integers. So we have some conversion to do. Let's take the bits that we are asking about as 3 and the state as 10. It'll be apparent in a moment why I want these particular example arguments. Now, these are then encoded as normal numbers, but we need to know what the individual bits are in the binary representation. In order for all the bits to line up, being that 10 would otherwise be a wider number than 3, it's important that we convert them together. So, together, let's concatenate them together. And now we can convert them to binary. We could take a fixed width representation and convert them to that, but we can also let APL determine how many bits are necessary for the widest one of the two bit patterns. We do that by using the opposite function, the one that would convert from the bit patterns to numbers, and running it in reverse, that is, applying it -1 times. So this is the power operator applies functions n times, and this is applying it -1 times. And the way this parses out is it's called a fork. It means we apply this function to the arguments 3 and 10. That gives us the vector 3, 10. And then we are applying this function, which is the inverse base evaluation, that is an encoding to base 2. And what we get here is one column per number. So this is our 3, which fits. This is 1 times 1 plus 1 times 2. That's 3. And 10 is 0 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8. So 2 plus 8 is 10. And now you can see why I chose these particular arguments. It's because then we have all the different combinations of bits on the left and bits on the right represented. Here we have 0 with 1 and 0 with 0, 1 with 1 and 1 with 0. And what does this mean that we're querying whether these bits are set? It means we aren't interested in all the bits on the right. We're only interested in the bits that have a 1 on the left. And in that case, we must also have a 1 on the right. So, if we go through all these possibilities, we can see that a 0 on the left and a 1 on the right, that is fine, that is okay. A 0 on the left and a 0 on the right, that is also okay, because it doesn't matter if there is more state than what we are querying. A 1 on the left, a 1 on the right, that is also okay, but a 1 on the left and a 0 on the right, that's not okay, because that means we're querying a bit and the bit isn't set, so the answer is no. Our requirements haven't been met. So now we need to find some way to process this matrix to figure out if our requirements are met. And I think maybe the easiest way to reason about this is to do the opposite and say, let's look at when our requirements are not met. And that was only in this case. So being that our domain is restricted to the booleans, 1s and 0, this is the only case where the left side is greater than the right side. See, here they're equal to each other, and here they're equal to each other, and here the left is less than the right. So it's only the case where the left is greater than the right that is problematic, which means, conversely, that all the cases where it's not less than, when it's not greater than, and so all the cases where the left is not greater than the right, those are okay. So what is not greater than? That is less than or equal to. Let's verify this. 0 is less than 1. 0 is, well, not less than, but equal to 0. 1 is equal to 1, right? But 1 is not less than or equal to 0. It's not less than 0, it's not equal to 0. So the next step is going to be to reduce over these rows. That is, we are inserting a less than or equal to between the elements on each row. And we can do that with a last axis reduction. So we have less than or equal to reduction. And this tells us that for the first 3 bits, our conditions have been met. It's actually only a condition in the 3rd bit here. But the last one is a failure. That doesn't really matter here because all we need to do now is to check if they are all met. We're not interested in the individual bits. So instead of doing a single reduction, we're doing 2 reductions. An AND reduction after we've done the less than reduction. That tells us that the requirements are not fully met here. Okay, this is our solution. Let's give it a name. And now we can try it. Is 3 met in 11? Yes, it is. And that's because 11 is just like 10, but with an extra 1 bit at the end. So both of these required bits are met. What about 4 in 11? No, because while we have a 1 here, we now have in 4, we have 1, 0, 0 here. So that 1 lines up with 0 over here, and then it isn't true. And that's all. Thank you for watching.